Welcome friends to the 10th module of AI. We will be discussing about the backpropagation algorithm that we mentioned in the previous module. The backpropagation algorithm is one of the most commonly used algorithm, and that's why we are going to stress about how that functions and how one can use that algorithm for solving problems which otherwise not possible to be used, not possible to be solved by other means. There are some problems. For example, finding out a right set of, this is quite interesting, right set of motivational strategies for employees. Suppose if you have a company where there are thousands of employees working and you would like to retain them, and this is a serious problem in IT actually. So what you do is, as an HR manager, you would like to have strategies designed and defined to make sure that they have more tendency to retain in the organization. For example, after 3 years of service, you probably give one foreign trip with spouse to every employee, or you have, if you have 2 children, you pay the school fees for those 2 children, and the other cost you bear those costs, and so on and so forth. These are called motivational strategies. Now what set of motivational strategies will be able to actually retain the employees? Now you would like to learn about them, so you may write a program to do it. In fact, one of my PhD students did exactly that. So this is an example where you can use backpropagation neural network. The other one, which one of my students did in his project, is he was working for a place where a lot of resumes flowing in daily. It's a huge company, and a lot of resumes used to come, and they have to have huge bunch of experts to look at those resumes and shortlist resumes for further processing, and that was very time consuming. So what he did, he wrote a neural network based program. So every day there are 5,000 applications coming in. He shortlists 500 out of that. So experts will have to look at only 500 resumes, and out of which they may figure out that this 50 are good, or 100 are good, 120 are good. So that neural network program could do it. So this is the other example which neural network program can solve. Fingerprint recognition probably is something that you have seen quite a lot in recent days. You just place your thumb on the device and it recognizes you as the person or doesn't. So that is again an example. This is again an example where backpropagation algorithm is used. Voice recognition systems and face detection systems, and there are many similar systems used in practice, which in sense using backpropagation algorithm. For backpropagation algorithm, what you need is a multi-layer neuron, multi-layer neural network, which anyway I discussed about that in the previous module, and we are going to study that thing in a little more detail in this particular module. Multi-layer module means that network contains more than one module, more than one layer. So and usually most of the neural networks use 3 layers, but the recent trend is to use many layers, hundreds of layers. The algorithm works like this. So there is a layer 1, layer 2, layer 3. The inputs come from this side and flows through these layers and then goes out from the last layer. So the inputs flow in the forward direction, and whenever the input flows, the output layer checks whether the output is right or wrong, and if the output is wrong, it floats those errors back, and that's why, because of this, the algorithm is known as backpropagation. It propagates the errors back. When the errors are propagated back, the weights are adjusted accordingly, which we discussed in the previous module. Now we are going to study in a little more detail. So this process, the algorithm which does all this, the algorithm tells how you calculate the hidden layer. Is called activation, what flows from the middle layer to the final layer, and so on and so forth. So that algorithm decides. It also calculates the error coming back, and so on and so forth. So the algorithm, the backpropagation algorithm, is all about processing like this. But there are some prerequisites to backpropagation. The first prerequisite is it works. In fact, backpropagation is used in many forms in many places, but the one which I am talking about, backpropagation neural network, the BPNN, which is the most used algorithm, requires the network to be complete. What does that mean? The first layer connects to every unit of the second layer. The unit or neuron are number of neurons. So for example, the input layer, we have 5 neurons, 1, 2, 3, 4, 5. Middle layer, you also have say 3 neurons, 1, 2, 3. Now the first neuron here connects to first, second and third. Second also connects to first, second and third, and so on. That means it has complete connections. Every input unit or neuron is connected to every middle unit. Okay, the same way every middle unit is connected to every output unit, and if it has more than one layer, the same thing is applied. So that is called complete network. So that's the first requirement. There is a figure 9.1 in the handout as well as in the PPT, which clearly visualizes what I just talked about, and this is called 332 network. It can be any. So here we have 3 inputs, 3 hidden or middle layer units, and 2 output. How number of inputs and output unit and the hidden unit are decided, we'll soon see. But before which, let us try to understand this thing, this multi-layer feed forward. This is called feed forward. Now that's the other word which is being used. Feed forward means the inputs are flowing in the forward direction. Remember, it applies back propagation algorithm for learning where the errors are propagated back. So the point is, inputs are flowing in the forward direction, the errors are flowing in the backward direction. Okay, so that is the essence. So that's why it is called feed forward network. The information is coming in the forward direction. The figure clearly indicates how it is moving, because it's moving in the direction of the arrow. Okay, and you can also see that this is a complete network. Every input unit is connected to every middle unit, and every middle unit or hidden layer unit is connected to every output unit. Now, how it learns, in fact, there are 3 examples shown on the screen. It's a 9 into 9 matrix, and I'm talking about a very simple case, 9 into 9 matrix, and I want to recognize A. Okay, so that is a very typical problem that I've taken. This could have been a 500 to 500 or 5000 into 5000 pixel image where there is a signature. The discussion becomes little more complex, but the same. Okay, the process is the same. In this case, we'll have only 81, 9 into 9 is 81 inputs. In that case, is 500 into 500 inputs, and so on and so forth. So the network becomes little big, pretty complex, but the process is going to be the same. You can see that these 3 A's which are shown here are quite different to each other. They are not same. So these are the A's which are provided to the system, and you can see that in this case, some of the, it's pretty crude representation, but it's still possible for us to understand how it works. You can see that it is, there are some pixels which are on, there are pixels which are not on. Okay, so every image contains some pixels which are black, some pixels which are white. Okay, based on this, the inputs are provided to the back propagation algorithm. And there is an example shown on the next slide. Look at the second figure and look at the data which is generated from that figure. You can see that everywhere there is a white cell, we have 0. Everywhere there is a black cell, we have 1. Now this is how it is generated. Now this information is to be provided to the backpropagation neural network. You can see that there are total 81 inputs, out of which some of them are zeros and some of them are ones. Okay, so the next slide talks about this process in little more detail. Begins with 81 as 9 into 9 total inputs. Now every input of A will be 9 into 9, total 81 will use. Okay, so that is x1 to x81 information provided. Okay, so every A contain 81 inputs. Obviously, I want to identify not only A, but if I am interested in finding out all uppercase letters, so it is A to Z, that means 26. Okay, so I have 26. In that case, I need outputs, total 26 outputs. If I also include zeros and ones, I need 36 outputs. If I also want lower and uppercase, it is 62 total. So what I need is either 26, 36 or 62. How many output units do I need? In fact, there are many ways of doing it. One very simple method is to use normal way of using binary neuron as a single digit. If you do that, for 30 less than 32, 5 units are good. So 2 raised to 5, you can have total 32 combinations, which is good. For example, all zeros will be 1, all zeros but the last one is B, and all 0 but the fourth one is C, and so on and so forth. So you have those values differentiated that way. Want more, you can even add one more. So if you have 6 units, you can have total 64 possible output. So based on this, we decide number of output units. In this case, 81 input units, because it's 9 into 9 matrix. The output units will be 5 or 6. How will you decide the hidden layer? The hidden layer number of units, people have worked on and decided that the best value for hidden unit, number of hidden units can be calculated by using geometric mean of input, number of input units and number of hidden, the output units. That means multiply both of them and take a square root of it. In this case, you can see that on the slide that we assumed output units to be 6, the input units 81. So, you multiply them and take a square root of it, comes near to 10486. So, you take a square root of it is nearly 22. So, number of hidden units you need are 22. So, in fact, you may see that why the hidden unit is provided. Let me tell you that neural networks began when there was no hidden unit. There was only one unit which is input, there is one unit which is output. There is no, in fact, there is no input unit, there is no hidden unit there. There is nothing which is called single layer perceptron. And initially it was considered to be a very good thing unless somebody found, there was a guy called Minsky who found that however good this neural networks are, they are incapable of solving some problems which he called non-linearly separable problems. Those problems include a very simple problem called XOR. If you use only that single layer of perceptron, it cannot, or perceptron or neural network, it cannot, Minsky, researchers used to call it perceptron. They say that it is impossible for such a network to even differentiate between the values which are XOR. So, it cannot even solve that problem. So, people started thinking that neural networks cannot solve this problem. Almost 20 years after long period, somebody could find multi-layer perceptron, multi-layer neural network and could actually demonstrate that it can solve almost every problem that comes across. In fact, it is possible for a neural network to solve any problem it can learn. Now, the question is whether it can learn or not, that is one thing, but it also is, theoretically it is possible that it can learn. It is also possible that, in fact, empirically it has solved many problems, but again theoretically if you want a proof that a problem is given will surely solve, that is not possible. It was possible in the single layer version, but the multi-layer version you do not have that promise. Fortunately for us, the empirical studies, the practical solutions to this problem proved that it is actually possible for almost all cases. So, we do not need to bother much about the theory issue. And there is one more thing, as I said that here we have one hidden layer. You can have multiple hidden layers also. One hidden layer, the idea of having a hidden layer is to provide some means of finding out features of the input. We will soon see, but for example, capital A contains 3 different features, one slanting line like this, the other slanting line like this, one more is a horizontal line. Whenever these 3 features exist, we assume that it is A, irrespective of the size or orientation or wherever it is. Okay. So, if you can do that, what is the advantage? The advantage is that we will be able to generalize any size A, any orientation, anywhere. If you got 2 different slanting lines in different direction and a horizontal line, it is A. So, that can generalize. So, the beauty of having a hidden layer is that it can figure out the features from the input, and based on those features the output unit can learn to become active or inactive. It is possible to have multiple hidden layers, and again the theory says that it is possible to use a single hidden layer, and a single hidden layer can do a job which multiple hidden layers can do. So, it is something which says that one single hidden layer is suffice, is good enough for solving any problem. But then later on researchers found that if you want to if you have a very complex figure where a feature itself is made up of other features, what you need is multiple layers. And today, as I said, there is something called deep learning which is happening where you have a lot of layers, and there is a modified algorithm, not BPNN is not used, a little modified algorithm is used there. And as I said, the algorithms are not foolproof. The algorithm may not correctly classify. In that case, in most cases you will have to rerun the program. You may be surprised rerunning the program how it solves, because as I said, you begin with random set of weights. If you look mathematically, a random set of n weight is a point in an n dimensional space. Obviously, we want to get the correct values of those n inputs which can identify every input correctly. So, that is another point. So, what you need to do is to travel in n dimensional space from the random point that you start with to the goal state. The issue is that if you run the program again, you will pick up some other random point and start traveling towards goal state again. Now, if there is a local minima, local maxima, whatever, when it is moving around and it falls into local minima or climbs up local maxima, it cannot go forward. But if you run it again, it starts from some other point, other place on the same plane, will probably be able to reach. Okay. So, that is the reason why what you need to do is to rerun the program in most cases and will solve your problem. Well, the next slide talks about how hidden unit learns to be active. For example, I have 3 inputs A, I and H, and I am showing 3 different images of A, but 2 images of one H of I and H. Okay. So, there is a unit 1 which learns to be active when the line, one slanting line from going up from left to right, okay, is present in the image. One more line, one more hidden unit learn to become active and it is right, is going down from right to left to right. Third unit will learn to become active when the horizontal line is. You can see that the second slide, that the hidden unit which learn to active when there is an horizontal line also learns to be active when there is I and there is H. Okay. So, it is possible that the different hidden units learn to remain active when there is a typical feature present in the file, present in the image. How output unit learns to remain active when for example, A is provided to it is again pretty simple. It just look at the hidden unit which it will just look at 3 hidden units, one slanting line, one with the this one slanting and the other one is on the other slanting, and the third one is the horizontal, left to right up, left to right down and horizontal. When these 3 lines remain active, is these 3 hidden units become active, the unit which wants to learn to become active when A is presented will learn to become active. So, okay, so that is how it learns. You can see that the third unit learns to become active when there is the other line. So, the figures, the 3 figures in the handout as well as the PPT clearly indicates this part. Let me recap this part is pretty important. We have 3 units, one learns to become active when there is a slanting line moving from left to right up. There is the other slanting line which moves from left to right down, and the other one which is horizontal. Every unit learns to pick up this feature and learn to become active. So, when there are many other cases, for example, in case of G, okay, you also have here you have a horizontal line. The issue is that in case of G, if in most handwritten case recognition, you will not find that horizontal line, but in case of A, you will almost invariably find them. So, these are also points that one must learn, but it is very interesting how backpropagation manages it. What you are supposed to do is to provide some images of G with and some images without that horizontal line. So, it learns to accept G even without that. So, it is very important that you provide right set of samples, right set of images, and that is why we have to provide number of images. Okay. So, more numbers you provide, in most cases it is better, but then there is a limit also. You should not be going beyond that limit, and we will be discussing about that soon. Now, let us look at this backpropagation network. Now, this backpropagation network is depicted here with the dark bold face lines and the weights. You can see that there are, now this is only an extension to what we have seen in the earlier module. We have x0 to xn as an input. Now, the n value depends on the features that you take from the input. We have already seen that. In our character recognition case, the n value is 81. Okay. Then you have the middle layer. Remember, middle layer you have total m units, and remember in our previous example that we took, m value is 22. Okay. And you have output units. In our case, it is here I have taken L. So, L number of output units. What is the value of n in the previous example? 26 if we only consider uppercase, 36 uppercase plus the digits and 52 when you consider upper, lower case and together, and 62 if it is upper, lower case as well as digits. Okay, so we are considering L to be 6, then all three cases are possible to be provided. Okay, so you can use them. Now, look at the weights. Okay, now those weights, remember every input unit is connected to every output unit. So there is a weight between x0 and h1. There is a weight between x1. Okay, remember the x0 and h0 look like inputs, but you can see that there is no arrow going inside. They are not inputs. x0 and h0 are 1. Okay, remember W0 indicates threshold, the negative value of threshold. Similarly, H0 also indicate the W0 in that case, H0, the second layer. Okay, so that also it is the negative value of threshold. Now there are two different set of weights. Okay, there are in other words there are 3 layers of inputs, but 2 layers of weights. So the first layer of weight is called W1, the second layer of weight is called W2. The first layer, and you can say W1 prefix is all weights. Okay, the value which comes next, the suffix 01, that value indicates which input unit to which output unit. For example, W101 means a weight between 0th input unit to first hidden unit. W201 means the weight between the 0th or the first hidden unit to the output unit 1. Remember that is what the indication is, and that's how it is done. Now how it is summed up, remember the calculation we requires everything, the sigma that we have seen, x1 W1, x2 W2, x3 W3 and so on, and when you consider the threshold you also have x0 W0 where x0 is basically 1. So the summation, suppose if I want to calculate the sum that is happening at h1, how it is calculated is shown in the next slide. You can set h1 equal to, why it is 1, because x0 is always 1, into W1 01. Then W plus, now you talk about the next input, x1 into W1 11, x2 into W1 21, x3 W3 1, okay, so on and till the last one. And remember total values are m. Okay, so we have the last one as W1 M1. Okay, similarly at ith hidden unit, it shows on the screen, the only difference is that it was 1, the second suffix was 1, which becomes I now. Okay, so that's the only difference, otherwise it's the same. Okay, so that is basically summation. And how hi values are calculated, we have already seen that we'll use sigmoid function. Sigmoid function is used here. So there is 1 upon 1 plus e raised to minus summation, and the summation we have already seen. Okay, it shows that j equal to 0 to n. Okay, the hidden unit, total n inputs are provided, n inputs are presented, so it is 0 to n. Okay, and what you add xi wi. Okay, so those xj and wj are multiplied. Okay, so that is what is being done here. Same way the output unit, all inputs, all hidden units connected to it, they are all multiplied, hy wi, hi wij, in fact ij, if this is the jth unit, hi ji, h1j, assume this is j, h1 w1j, h1 w2j and so on. So it calculates it that way. So total summation is calculated. In same way 1 upon 1 plus e raised to minus sum is calculated, which you can see on the screen. So we call them equation 10.1 and 10.2, which indicates the output generated for both of them. With that, we'll come to an end of this particular module. We have looked at backpropagation algorithm, and this is all the this is prerequisite to backpropagation algorithm. We'll see in the next module how exactly backpropagation is going to solve the problem, but this even the algorithm, we'll look at the complete algorithm in the next module. In this module we have seen that how this thing is divided into layers, how the activations flow, how the values are calculated, how the weights are named. W1 is layer 1, W2 is layer 2, I and J. So, I the input unit and J hidden unit, W1 Ij, W2 Ij is ith hidden unit to jth output unit. Okay. We have also seen how you decide number of input, output and hidden units. Number of input units is decided based on the input, okay, the size of file that you take for input. Number of output units depends on number of outputs that you would like to classify. Number of hidden units is taken as a geometric mean of input and output. Okay, so and we have taken a character recognition example. The job of a hidden layer is to identify features, okay, and that will help in generalization, because if you identify features irrespective of the input the pixel value is, it becomes possible, it makes it possible to generalize. For example, here you get a slanting line like this and a horizontal line, you can call it a irrespective of which pixel it illuminates and which pixel it doesn't. Okay. So, with that note, I would like to conclude this module. Thank you all.